webinar. Uh, and can everyone hear me? Just let's see the chat. Can you guys just let me know if everything's working? Okay, great. So yeah, thank you guys all for joining. And thank you for joining this workshop. I'm first going to start by doing a little bit of an introduction as to who I am, a little bit about my background. So I graduated with my bachelor's and my master's in mechanical engineering from the New Jersey Institute of Technology. There, during my time, I specialized in thermal fluid systems and energy. I did my undergraduate and graduate research on thermal management of solar cells, so simulating a lot of physical and different physical environments involving electronics, optical properties, thermal properties. Additionally, I've also done a few internships in both aerospace and nuclear fusion. So I interned at NASA for a couple summers where I did a lot of work with mechanical systems that take different measurements of thermal properties as well as optostructural characteristics and principles. So I did some stuff with that. I've done some stuff with superconducting magnets. So I've kind of been all over the place, but at the core of what I do, I'm really just interested in mechanical engineering principles that deal with thermal and fluid systems. So during all of my different projects and internships that I've done, I've definitely used a lot of coding, both Python and MATLAB. But specifically Python, I've seen in all of the industries I've worked in, from research to actual internship experience. So I really encourage learning Python because it has so many different applications. It's so widely used. And it's also a really great resource because of how many people do use Python. And so you'll see that there's a lot of third parties that will share their work. So it's a very collaborative platform. It's used in technological industries across the world. It's used in companies like Google, Amazon, Facebook, all the way to finance and entertainment, science, like I mentioned. It's used at NASA and in a bunch of other places as well, especially in research. So it's free to download. There's no barrier to entry. And like I mentioned before, there's a lot of libraries that exist because it is a free resource, and because so many people use it. On top of that, I guess something a little bit more topical is that it's also widely used in machine learning, which is a very hot topic right now. And today we're actually going to be delving into very basics of machine learning, but it just goes to show how varied of a resource it is. There's so many applications, and the sky is really the limit. So you can be creative as you want on this coding language. So with all that being said, these are some reasons why I think everyone should learn Python. And hopefully today you guys get inspired, you guys learn a little something, and you can take what you learn and continue to expand on it. So, how this is going to work is, as Mia mentioned, there is a Google Colab that you guys should all be able to access, and I'll be taking you guys through each box. So we're going to be going in order, and you guys are going to run it on your own and get to see, hopefully on my screen, what I'm doing, so you'll get to follow along. And I'll be taking you through each line of code so that we can look into what the code is doing, why it's relevant, and we'll be building our knowledge little by little throughout the webinar so that towards the end, we'll be analyzing some data. And along the way, I'm going to be introducing some basic mechanical engineering principles and also hopefully giving you guys some real world context so you can understand the importance of what we're doing, but just also good mindsets to have while we're coding. So yeah, let's get started. Let's get started with lesson one, Python as a calculator. And we are going to run the first block of text and look at the first function we are going to see, which is the print function. So once you run the text, you should be able to see the script hello world, as well as a second line that says class string. So let's start with the print function. What is the print function? It's a function that allows us to display different data types in Python. And the importance of this is that we get to see what the computer is doing in real time. It is just generally a way to communicate with the computer. As you can see, you can just drop text in there and get it displayed, but also as we'll see as we continue to go through the lesson, we can also display variables and expressions. So it's just a really great multi-purpose tool to see exactly what you are doing to interact with the computer. And then the second line, you see that we also have a function type. The type function is embedded inside of the print function. So we get to print out the data type that we're looking at. And the importance of this is because we want to know exactly what data types we're using as we code. If you look at the text underneath this first box, you'll see that I have listed different data types in Python. And what's important about data types is they define how data are stored and is stored and operated on. So for example, how we use our string data is going to be different than how we use our numeric type data. And as I mentioned before, we're going to see how this gets used throughout the webinar. The data types we'll mostly be concentrating on are the text types, the numeric types, sequence type, and mapping types. But overall, we are able to see the type of data that we're working with using this type function, which is again another good way to interact with our code and make sure that we are using the programming logic that we're using is what we want. So now we're going to scroll down to the next box where it says basic arithmetic using operators. We're going to run this one, and using our print function, we're going to get to see what our results are for these expressions. Now, the operators that we're using are very straightforward for addition, subtraction, multiplication, and division. As you can see, we have in our outputs some different formats that we're getting, right? We have our first output, our first line of output has parentheses around it, as well as a J. Some of our other outputs are just whole numbers. And then on the fourth line, we have a number that has a decimal point. So if we now run the next line or the next box of code, we're going to get to see exactly why the format is a little bit different. And it all goes back to what we were talking about before with our data types. So over here in our addition, we are adding this number 2j. And in Python, the j indicates an imaginary number. So this added with the 1 gives us what we consider a complex data type within our numeric type. And so we have our complex data from that expression. We also have our integer values. So these are just whole numbers. It can be positive, it can be negative, or 0. So numbers we're very familiar with. And then if you see the result of our division expression, we have a float value. So this is where the decimal comes into place. And as an engineer, normally we're dealing with mostly float numbers. However, you may see some complex numbers thrown here or there. So again, just notice how our print and our type function really come in handy because we're able to see the result of our calculation. But on top of that, we're also able to see what our data type is, specifically within our numeric types. And very straightforward operators, nothing to be scared about. Python also uses the same logic as PEMDAS, so the order of operation is the same as what you've learned in school. And now we're going to go to our second part. So now that we know how to do some basic math, basic arithmetic, we're going to start creating variables, which we can use to save the result from these expressions. And so something fun, this is where we're going to do some very basic engineering. One of my favorite lessons or one of my favorite topics in engineering is heat transfer. And so today we're going to be solving a very basic heat transfer problem. Now, within heat transfer, there are three main methods of exchanging heat. We have conduction, convection, and radiation. But today, you don't have to worry, we're only going to be focusing on conduction. So, conduction is a transfer of heat within a stationary medium. Think of it like temperature that moves from one side to the other side of the wall. if you have a temperature gradient, this is what drives the heat transfer. So if you have a higher temperature on one side, of course, it's going to want to disperse towards the side with lower temperature and reach an equilibrium within the medium. So there are a few different variables, a few different numbers we want to consider when we are calculating for this heat transfer. And we're going to be specifically calculating the rate of heat transfer. And this is measured in units of joules per second. This just signifies that it's the rate how fast heat is transferring from one side to the other side of a medium. So we're going to be looking at a very basic two-dimensional wall today, and we're going to be calculating how fast heat travels from one side to the other side of the wall. So to be able to do this, we have to first define a few variables, which we are going to do in this box here labeled creating variables. We're going to run it really quick, and we are going to see that we're not going to see an output, right? Because we didn't use the print function, but we're soon going to see if our variables were saved properly and if we use them in the next line of text. But first, let's kind of go over some of these variables and what they mean and represent. So over here, I've defined a K glass and a K brick variable. Also, something to note here is I don't know if you guys have noticed this yet, but I'm able to add comments to my line of codes. I'm able to do this using the hashtag that you see. So as we run it, the computer is not reading what is coming after the hashtag. So this allows us to put really helpful notes within our code. It's really good for whenever you step away from code and want to come back to it. It helps you remember what you did. For example, I'm adding the names of my different variables, what they represent, but I'm also adding units, which is able to help me if I want to verify that my calculations are checking out and making sense. So that's just something to know when you're coding, really useful tool. And additionally, as we make these variables, we also have to keep certain things in mind. So there are rules to naming variables. Variables can only be made with characters from A to Z. They can contain numbers or an underscore, but nothing else. There can be no spaces between characters. Additionally, they must start with a letter or an underscore character. They can't start with a number. Variable names are case sensitive, so an uppercase K is going to be different than a lowercase k variable. And additionally, variables cannot be named after Python functions. So this is just going to be something that confuses the computer, so you can't name a variable print. So these are just things to keep in mind as you go making your variables. So now going back to the variables that we made, I'm going to save what is the conductive coefficient of glass and the conductive coefficient of brick. So if we go back to our main problem, for each material, they are going to have different rates or different propensities for transferring heat. So if you notice, our houses are made out of brick and not glass. This is for multiple reasons besides transparency, but one of them is that brick is actually better at isolating your house environment from the outside environment, right? From the elements. We see this in the wintertime, in the summertime. There is less heat that is either entering or leaving your house because it's made out of brick. Whereas for glass, we don't really use that much glass in our houses, just for windows, for visibility, that sort of thing. So the conductive coefficient basically just describes how easy materials can transfer heat through them. So brick can transfer heat at a slightly slower rate than glass, which is why our glass coefficient is going to be a little bit higher. And now some other variables that are important in this calculation. We want to know the initial temperature between the two ends of the wall. We're looking at a two-dimensional wall, so we're just going to be seeing how heat transfers from one side to the other. Think of it like side A and side B. We need to know the thickness of the wall, right? The length or the distance that heat will be traveling. And we also want to know the surface area of the wall. So if you think of it like side A and side B, the surface area is going to be like if you split the wall in half and got to see the cross section of the wall. So we're going to label all these different variables. We're going to include the units. Again, we're going to just run it one more time, and now we're going to move on to the next block of text. So now that we've created our variables, we can call them. And we're also going to be using our operators to do some very basic calculations. So to be able to calculate the heat rate, as I mentioned, we're going to need the conductive coefficient. We're going to need the surface area of the wall, the difference in temperature, and the thickness of the wall. So the heat rate is going to be directly proportional to the conductive coefficient, to the surface area, and to the difference in temperature. If you increase any of these numbers, then the heat rate should also increase. Now, if you increase the thickness of the wall, the heat rate should decrease. And this should also intuitively make sense to you. The thicker the wall is, the slower heat is going to be able to transfer through it. And the higher the conductive coefficient, the higher the surface area, and the higher the temperature difference, the more heat should be able to move from one side to the other at a faster rate. So something important whenever you're coding, whatever your application may be, it's just important to check your coding logic so that when we have our output, so if we run this block of text, we're going to see that the heat rate of a glass wall is higher than the heat rate of a brick wall if they have the same properties, if they have the same thickness and surface area and the same temperature difference in between them. So intuitively, this should make sense to us. And this is why it's important to use the print function to get to display your results. So if you look at exactly how we do that, on our third line of code here, it says print, and then to be able to display our variable, while still also getting to label what our variable is, you can put the text in quotations. So you see here in quotations, we have the heat rate of our glass wall, the heat rate of our brick wall, and then we use a comma to separate our text from what is going to be our variable. And here we call the Q cond or the conductive heat rate of the glass and the conductive heat rate of brick. And that is what gives us our output at the bottom over here. Something else to note is that variables aren't only used to save numerical values, they can also be used for string text. So we have here our glass and our brick. And we can print this by just calling on our variable. And additionally, we can also add these two string texts together. So just different things that you can do. Like I mentioned, Python is great for creativity. And this is just additional capabilities that you have with variables. So now that we've sort of established some very basic operators, basic functions, how to assign variables, now we are going to be moving on to data containers in Python, what they are and why they're useful. So let's take a look. And we are going to start now with our box that says creating lists, dictionaries, and arrays. So I'm just going to play this or run it, and you're going to get to see the output. Now, lists and dictionaries are two different data structures, and they are important because they can hold multiple data points, which we can then use to store and manage and call and operate on information. Right, so now we have assigned some variables. Let's create a list with these variables in it. So we have our k underscore list. We're going to set that equal to square brackets. And then within those square brackets, we are going to include both of our conductive coefficient values. So we're going to have k underscore glass, k underscore brick. And now we're going to be creating our dictionary. So we are going to label it k underscore dict, and then we are going to set that equal to squiggly brackets. And then we are going to be assigning something called a key value pair. So this is what differentiates dictionaries with lists. With lists, you can basically just store variables as many as you'd like, or obviously within the confines of what your computer can store. But for K lists or just lists in general, you're able to store different data types. So you can have numeric data types, you can have your text data types, you can have your logic data types, you can mix and match. Whereas with the other structure we're going to be looking at, arrays, it's going to be a little bit different. Now for dictionaries, you can also store different data types. As you see, we have a string data type alongside a numeric data type, but it operates on a different principle. So here with a key value pair, you're able to assign a key, which in this case would be glass or brick. And that key is going to be linked to a value. So for our key glass, our value is going to be the conductive coefficient of glass. And then for our brick key, it's going to be the conductive coefficient of brick. And so this allows us to link our key and our value, but we're not simply confined to these two values, whatever they may be. You can also embed dictionaries, meaning your value in a dictionary can be another dictionary or another list. So you can embed it that way and you can use it to store more information in your dictionary with multiple key value pairs. So again, lists, dictionaries, and as you'll soon see, arrays are good for different applications. Whatever your code may require, you should choose it accordingly. So now that we've been able to define our list and our dictionary, we're going to be printing them. And as you can see from the output, our list just simply has our variables named or displayed. And then our dictionary has not only our variables, but also our key. So our key value pairs. And for our dictionary and our list, you'll see that all of our all of our values are being separated by a comma. Now, if we print the next box, we're going to see that we can call upon different values in our lists and our dictionaries by calling on them with square brackets. Now, for our lists, you'll see that we use a numeric index starting at 0. This is important because in other coding languages, you might start at a different number. So, for example, I also use MATLAB a lot. And in MATLAB, you actually start at 1, you don't start at 0. So when I'm switching back and forth, I just need to keep that in the back of my mind so that I'm not calling on an index that I don't intend to. Now, for dictionaries, actually, what you're calling on is your key. So that's why we call it a key value pair, because to get your value, you need to call upon your key. So in this case, we also have our the name of our dictionary and the name of our list, and then following that are the square brackets that we're going to be using to call the value that we want. So now if we hit play, you'll see that this is how we can call our glass and our brick conductive coefficient. Now, this is something that if you're following at home, I also have now included 2 lines of code or 4 lines of code that we're going to be using to actually add values to both our list and our dictionary. So if you're following at home, you can write down this code just as you see on my screen, and we are going to be using it to add a value. Here we're going to be using dot append, and this adds a value to the end of our list. And then we can also now print our list to see how it's added to our list. And we are going to do the same exact thing for our dictionary. The format's a little bit different. You have to call on your dictionary with square brackets. You're going to add the new key that you want to define, and you're going to be adding the corresponding value by setting it equal to what you see is at the first part of this statement. And now our new value at the end of our dictionary is going to be with the key new value. And it's also going to be equal to our new conductive coefficient, our hypothetical conductive coefficient that we're now adding. Right? And now we're going to be learning about the last data structure we'll be focusing on today, which is an array. So we're also going to start off by importing a library. Now, the NumPy library offers optimized capabilities that we get to now use in our Python code, and we are going to assign it NumPy as NP. Now, NP is what we call an alias, and it's basically a nickname that going forward will allow us to use capabilities from this library by only having to write NP. So it's shorter, like I mentioned, a nickname, something shorter that we can use very easily. So if we run this box of code, you're going to see that we use within the NumPy library np.array. So our array is going to be a data structure that we're using now. And arrays are a little bit different than lists because, as I mentioned with lists, you can have multiple data types, whereas arrays only offer homogeneous data types. So you can only put numeric types, for example. So when you run it, you are going to set your array equal to np.array, and then you're going to be using rounded brackets and square brackets within while you define your array. And so you're going to have your conductive coefficient of glass and your conductive coefficient of brick here. separated by a comma to indicate their different values. You're going to run it, and then you can now print it. So once you print it, you'll get to see the output of our array. And we're also going to be printing out the conductive coefficient of glass and brick, which you call upon the same way that you would a list. And just also so you can see, we're going to be appending our array right over here by using np.append. That's how you append a NumPy array. And in parentheses, you're going to see the array that we want to append, separated by a comma, and the new value that we want to add to the end. Once we print it, you see that the result is similar to our list up here. Where is it? Over here. And the more times you run it, actually, now that I notice this, the more times that you run it, it's going to just keep adding it on to the end. But that is the result from our list, our dictionary array. And syntax is super important when you code, right? Making sure that you are including parentheses, commas where they're needed, uppercase versus lowercase. So you have to be very aware of that as you're going through coding, as you're debugging your code. If you have problems, a little syntax error can go a long way. So I've recapped here the different data structures that we've gone over, as well as how to define your different values within those data structures. All right, so now that we have gone through that, we're going to move on to lesson 3, where we're going to do an introduction to our data. So now that we've defined variables, some operators, some data structures, we're now going to get to work with engineering data. And we are going to run this block of code, and I'm going to take you guys through it. Some of this may look a little bit confusing, but in its essence, I'm going to break it down logically what it's doing. So we're going to be looking today at some thermal power plant efficiency data. And this data I am getting from a site called Kaggle Hub, which is a free-to-use site. You just have to sign up, and you're able to access a bunch of different data sets that people will just upload on there. So as you'll see, I'm also going to be importing a lot of different libraries in this block of code here. And I'm going to first start by describing what some of these libraries do. So I'm importing Kaggle Hub because that's where I'm going to be getting my data from. I'm going to be importing OS. It's a module that allows us to directly interact with our operating system. And what this basically means is that we're able to navigate folders, create delete files and directories, and modify file paths in all the different ways that our computer looks for information. I'm also going to be importing Pandas, which is a library for reading CSV, Excel, and SQL data, for cleaning and filtering data, and all of the ways in which we will be converting data from one type to another. I'm going to be calling it as an alias here, as I mentioned before, a little nickname for our library, which is PD. And then I'm also going to be importing matplotlib. This is going to help us with visualization once we start to plot our data points, and I'm going to be calling that SPLT. I also have a module that I'm going to be importing for linear regression, which we're going to be using all the way at the end. But all in all, these are just some pretty common libraries that you'll see downloaded, especially when you are importing data into your code. So the next lines of codes may look a little bit overwhelming, but I just want you guys to know that actually the way you import data into your code may be different depending where you're importing it from. So for example, some of these lines of code are dependent on the fact that I imported from Kaggle Hub. So we're not going to get too much into the semantics of what all these functions are doing, simply because we just don't have the time today. But on top of that, if you are interested, I do encourage you to look more closely at these. Sometimes if you just hover over the functions, they'll tell you exactly what you need to know. But ultimately, because each manner of importing your data may be a little bit different, I really encourage you guys to use online resources to help you with that. That's actually what I use to help me learn how to import directly from Kaggle Hub onto this code. There's so many resources online, as I've mentioned. This is one of the reasons why Python is such a great resource, is because so many people have worked with it. And if you have a question, there is most likely going to be an answer out there. So instead of going just line for line like we've done before, I'm going to explain what the general idea of what I'm doing in this code is. So there's a few different parts to it. First, we're downloading the dataset from Kaggle. That's what you see here in the comment download latest version. And we are downloading directly from Kaggle, and we are going to print out the path to our files. Over here, you'll see it in the output. The first line, path to dataset files, Kaggle input, thermal power plant efficiency dataset. Great. Now we are going to be loading part of it. That's going to be the Excel file that we're loading. And this is just because that is the original format of the data. So if you go into Kaggle Hub, you'll see that that is what you can download. And now we're going to be converting it to a CSV file because that's what our Python code is going to be reading and extracting from. So that's why we need the pandas library, as I mentioned before. That's what we're going to be doing in this chunk of text here. And then as we convert it to our CSV format, we're going to be saving it somewhere usable. So that's why we have our CSV path. And then after all this is done, we are going to be showing what files were downloaded. And that is essentially what's going on here. So in a succinct way, we are going to be downloading our data set. We are going to be loading part of it, our Excel file. We're going to be converting that Excel file to CSV format, which makes it readable. We're going to be saving it somewhere useful in our path. And then we're just showing what files were downloaded when we use our print function, our print statement that you see here. So as I said, nothing to be scared of. This is all information that's very easily found online. And going forward, it's going to make our data set now usable so we can start to examine it a little bit. So before we sort our data set, we're going to be describing the data that we're going to be looking at today. So I have for you guys a thermal power plant data set. And a thermal power plant basically uses fuel from a boiler to produce high pressure steam. And so now this steam is used to spin a turbine, which as the steam expands within the turbine, it rotates, and that rotation is what causes electrical output from a generator. And now as this steam is cooled down, it is then compressed, and it then goes back to the beginning of the cycle where it is once again turned into high pressure steam. So as you can see, this is a closed loop cycle. And we have our input, which is the fuel that we use to heat up our water turn into steam. So that would be our input. And then our output is going to be the electrical energy that we generate from that turbine rotation. And so as an engineer, we are interested in our performance. So we're going to be looking at the efficiency of our system. And to look at our efficiency, we need to know what our input and our output is. So those are going to be the two columns of information that we're going to be downloading from our data set and looking at today. So if you go down to the block underneath, we're going to see that first we're going to sort our data frame. This is just going to be putting all of our X values in ascending order, so from least to greatest. And we're going to be using the sort value function over here. We're going to be sorting our DF, which is going to be our sheet of information, our data. And we're going to be sorting it by our fuel input energy. So that's going to be on the x-axis, think of it, of our data. So we're going to have our X and our Y, where we consider our Y, which is our electrical output, to be dependent on our fuel input. So over here, we're going to call the two columns of data that we're interested in while sorting them as well, which is why you see here the comments as variable call out. So we're going to be calling out our fuel input energy and our electrical output. And the reason how I know what these columns of data are called is simply because I looked on the information on the Kaggle Hub, and I looked to see the data sets I was interested in, or the columns of data within the data set that I'm interested in. So over here, you will notice that, well, first off, I also made sure that the length of the data was the same. This is just a logic check. As you can see, I use the len function of both the len function, which we use parentheses around the X and the Y just to see how many values are in our columns, and I'm going to print it. Again, another like litmus testing check. And then I'm also going to convert the fuel input from gigajoules to megawatt hours. And this is because when we're looking at efficiency, we want to make sure that the unit of our input and our output is the same. So this is just a part where I'm sort of pre-processing the data before we use it in our analysis. So this is where we have to put more of our thinking hats on and critically look at the data we're looking at, what our goals are with our data analysis, and how we intend to analyze the data. So over here, I'm going to simply convert the fuel input energy value. So I'm going to set the conversion rate to 1 over 3.6. That's the conversion rate from gigajoules to megawatt hours. And then I'm going to be redefining my x variable, and I'm going to be multiplying every value in my data set by this conversion rate. Now we're going to run it, and now we are all good to go. So now we're going to be moving on to our data analysis. And so this is where things start to get a little bit interesting and a little bit more critical. So our goal with our data analysis is going to be to target 3 areas. We are going to be looking at describing the data, identifying patterns, and making predictions. So we're going to start by looking at our mean and our median of our data set. And the way that we use these functions is we use our NumPy library again. So you'll notice that I'm using the alias in these lines of code, npy.mean, and then in parentheses, the column of data that we're looking at, our x and our y. And we're going to be setting our variables, of course, to our output, just so that we can print them out later and compare them. So just a quick review of what these functions actually are. So the mean is going to be the average of all of the values in our data set. It can be taken by adding all of the values and dividing by the number of values we have, right? So our average. And it's going to help us as we calculate our median. So the median is the midpoint or the numerical center of our data, right? There's an equal probability of falling above and below the median. And when we compare our mean and our median, the closer they are together, the more evenly distributed our data is going to be. And so we're going to be using this metric as we analyze our results. Now, if we print or if we run this block of text, we are going to be able to print out both the mean and the median of our fuel input and our electrical output. So now if we look at the print statements that we're using here, they're a little bit different. We are actually, the F here stands for the formatting that we're using. So when we call upon this F, we can change the formatting of whatever number or variable we are printing in this statement. And the quotation marks tell us that this is actually a string. This is not, this is being turned into a string value and is not a float value. But within the squiggle, we see that our float value has a semicolon and then .4g. So the .4g is how we actually change how many decimal points that we show, right? Because these are float numbers, they may have any number of decimal places, but we're only interested in a select few. So over here, I've put 0.4 to indicate that we're only going to be considering 4 significant figures here. And as I mentioned before, this is a formatting thing. This does not mean that the value itself only has 4 significant figures. It's just how many we ourselves are choosing to display. So now let's look at our results. And we see that if we compare the mean and the median of our fuel input, our mean is a little bit lower than our median, meaning the values skew a little bit to the lower end of our data set. And if we look at the mean and the median of our electrical output, we see that they are a little closer together, but they still skew a little bit. There's more weight towards the lower end of our data set. So now we're going to be moving on to the next section where we are going to be looking at our efficiency. So as I mentioned before, efficiency is calculated by dividing our output by our input. And we are going to be doing that for our array by using np.divide. And the difference between doing this and just simply using a division operator is that this allows us to divide every value in our array by the corresponding index. So both values in the 0 index for our y and our x columns of data are going to be divided by each other. The 1, 2, 3, 4, 5, and so forth, they'll all be divided by the corresponding value. So they have to be the same value. Basically, they have to be the same length to use this division operator. And we are going to have that be our efficiency. And now we can take this efficiency data that we now have, and we can also calculate the mean, the median, and the standard deviation. So the standard deviation, as a recap, is a way of measuring the variation in a set of values from the mean. So the difference between different values in a data set and their mean value, which in our case here says the mean efficiency is 1.309. And we're going to be getting back to analyzing this a little bit later. But our standard deviation of efficiency is only 0.135, which is pretty low. That means that there's not that much variation from the mean. All of our values are pretty close together. And we can further analyze our standard deviation by calculating our coefficient of variation, which gives us more of a standard way of looking at our results, right? These numbers may not mean much to us, but once we compare it using our coefficient of variation, it becomes a little bit more clear. So we calculate the coefficient of variation by dividing our standard deviation by our mean. And so the result is 0.1032. And this basically means if we have a coefficient of variation that is larger than 1, that means that we have a higher standard deviation. And if we have one that's lower than 1, we have a low standard deviation. So not that much spread in our data. And this is generally a good thing when we look at efficiency because if our system has very varied data at different points of use, right, for different fuel inputs, that means that our efficiency isn't very consistent. We want to have a consistent efficiency. But before we move forward and start to visualize what our data looks like, we also have to address the results of our mean and our median efficiency. So as you can see, our mean efficiency is 1.309. Now, if this value were multiplied by 100, because normally we also look at efficiency as a percentage, that would mean that our system has 130% efficiency. And this result should send red flags in your head because it means that our system is producing more output than our input. Now, this seems like it would be a good thing. However, in mechanical engineering systems, this means that something is wrong in the calculation because this is just not physically possible. With any system, you will always experience a loss, whether that be heat escaping or just an inefficiency in the system itself. It will never be 100% efficient. And this is why it's really important to, before you actually analyze your data by using visualizations or you go forward with using your data, you need to understand how to pre-process it or analyze it beforehand. That way you can ensure that the data makes sense, that it checks out with physical realities that you know and understand. And this is why it's important that as a coder, as an engineer, you always understand the basics of your code, but also of the engineering principles that you want to reflect in your code. And that's why it's just important to go line by line, always do sanity checks, always compare it with experimental values as well. These values, while they are coming from a data set, these are simulated values. So somewhere along the line, friction or heat losses must not have been taken into consideration. But all this being said, yeah, I just really want to stress the importance of understanding your data, where it's coming from, its limitations in your data, and always comparing it back to what you know and understand. So with all that being said, now that we've done our data analysis and we have our takeaways, we have our understanding of our data, we're going to be moving on to visualization and regression. So this is going to be the last part of the presentation, and we're going to reveal some of the features of the data, how to plot the data for further analysis, as well as visualization and making predictions. So first, we start off the section with seeing a polynomial function defined with and without an intercept. So we're going to be coming back to these definitions. I'm sure this is stuff that most of you have probably already seen before. Just your general functions, second order polynomial functions with your coefficients, with your x values set equal to your fx or your y. So now we are going to run this code and hopefully, I'm not sure if you guys had a chance to suppress or unsuppress these comments, but we're going to just start off with having our first section uncommented. And so once we run the code, we should be able to scroll to the bottom and see our figure, which is our thermal power plant input versus output. So this is just going to be a scatter plot of our data points. Remember, we have 10 data points total. And if we scroll back up, we'll see that we start off by setting our figure and our axis equal to this plt.subplots. So this function specifically, if you'll remember, PLT is our alias for one of our libraries. And this subplot allows us to define our figure and our axis. And so because this function has two outputs, we need to set it equal to two variables, which is why you see here the figure and the axis. And now we are going to be writing our lines of code. So we have a scatter plot that we're plotting. We call upon the scatter function with our x and our y, and we're also going to add a label. We want to make sure our figure is as descriptive as possible. This is also super useful for research because we want to make sure that anyone reading our figures are able to understand exactly what we have. And now we also set the X and the Y label, again, making sure to label not only the data that they're describing, but also the units. And then, of course, we're also going to be putting a title. So PLT title, thermal power plant input versus output. And then see here at the very bottom, we also define a legend because we'll be having multiple plots on this figure. And then we do PLT show so that we can ultimately show our figure. And so now we are going to be doing a very basic regression. So polynomial regression is a type of, it's a machine learning technique that we use to fit our data to some functional behavior. So we are going to be using a regression that solves the least squares method, which basically wants to minimize the squared error. And before I kind of explain what that means, we're first going to uncomment some of these lines so that you can visually see what we're doing before I explain it. So we're going to run this code. These are the lines that should be uncommented. And if we scroll to the bottom, you're going to see now that we have a line that is, or a function that is running through our figure. And we have labeled that normal polynomial fit. And so when we want to minimize the squared error in our regression, we are aiming to find two values. We want to find the sum of the difference between our data points, as you see here, the different points in the graph, and our line. And we also want to find the total number of data points in the data set. And so once we calculate these two values, the sum of the difference between the data points and our line is divided by the total number of data points to find the squared error. And so we want to find the least squared error possible to ensure that the line that we are plotting is as close to the data points as possible. So we want it to reflect our data as best as it can. And we can use a regression for this. So if you scroll back all the way to the top, you'll see that we define a polynomial function. So this is the function that you're seeing plotted here in real time. This blue line is basically being described by an fx function. And we have a second order function here, which means we have our x squared. And we also have three different coefficients here. You'll see the a, the b, and the c. So in our regression code, what it's doing is it's basically trying to find the coefficients that make this line as similar as possible to the data. So because there are functions that do this for us, as our functions aim to find the best A, B, and C possible, it's going to iteratively change the A, B, and C, right? Until it gets down to a number that we can call accurate enough, precise enough to our data. So the way we're going to be doing this in Python is we are going to be using the polyfit function, which is part of our NumPy library. Again, another reason why NumPy is such a great library to use. We are going to be including our, in parentheses, our X and our Y values, right? The data it's going to be fitting. And we are also going to specify what degree of function we want. So we could even put a degree 3, 4, 5 in here. Today we're only going to stick with a second order function. And then our output from that is going to be our A, B, and C coefficients. So now once we have our coefficients, we want to now construct the function so we can visually see how well our function is fitting to our data. So we're going to put those A, B, and C coefficients back into our poly 1D function, which makes our function for us. And this poly function, if you want to understand kind of like what it looks like, our y, our y fit is equal to just y, right? Our y value. And then our poly function is just the function, and this x fit is going to be our x. So these two lines of code, which hopefully you guys can all see, are essentially saying the same exact thing. So now to be able to have our x values, we are going to define a range of x values all the way from our minimum to our maximum. That is here in our data. So we're going to do that using the linspace function, which creates evenly spaced x values, as long as you put the minimum and the maximum of your x range, which you'll see here, x.min in parentheses, and then comma x.max. So that's how we call upon the minimum and maximum value within our data set. And then we're also going to specify the amount of data points that we want. As you see, we have a very nice continuous line. So we're going to put about like 200 data points. And now, as I mentioned that we have our x range, we can put that back into our function, and that's going to give us our y values. And then if we just go back over here, we'll see that we can plot the x and the y using x.plot, and we're going to label it normal polynomial fit. So you can see from our results that we have a positive correlation between our fuel and our electrical output. Now, because as I mentioned before, some of these results should be questioned because of the efficiency problem that we looked at earlier. It should also still make a little bit of sense, right? You're inputting, or the more fuel you burn or use in your system, the more electrical output you should get. Of course, as you can see, this line tends towards infinity. So we know logically too that if we had infinite fuel, would there really be infinite electrical output? For that, that's why it's also important to always compare simulated results back to experimental results, because they give you more of a reality check as to the limitations of a system. And so one more thing we want to consider in our data is another point, which is that in a physical system, if you have zero fuel input, you should also have zero electrical output. And we want our regression fit to reflect this, right? We want this physical reality to help ground our regression. And so what we're going to do is we're actually going to be grounding our regression by using a zeroed polynomial fit. So we are going to uncomment these lines of code. Oh, not that one. These lines of code over here. We are going to hit run, and we should see that there is now an orange line running through our data. And so we are going to be going over how exactly we can zero our polynomial regression. It's a little bit more of an involved process, but it is important to know. So we are going to be first building our design matrix without our intercept. So if we scroll back up to the top, we're going to see our polynomial function without our intercept, so no C coefficient, meaning that there is no y-intercept. The y-intercept is going to be at 0, 0. So now we are only interested in finding the best fit for our A and our B variable. And we are going to first build our matrix without our intercept. So we're going to be using VStack, which basically just lets all of our data be expressed in columns. And we are going to also use the transpose function because we want the format to switch the rows and the columns. And this is going to help us when we actually input it into the least squared function that we're using. So we're also going to define the x squared and the x value here. You see it's parentheses and then brackets again because we're looking at an array. And then we are going to plug it back into our function. And so this function lets us find the least squared method, similar to our polyfit. Again, this is going to be in the NumPy library. And once we have our x and our y, we can set that output equal to two variables. So coefficient zeroed, and then you see this asterisk underscore. And what this basically means is that there are multiple outputs for this function. So not just two, but the asterisk underscore allows us to dismiss all other outputs. We're not really concerned with them right now. We're only interested in the coefficients. So we are going to set our coefficient zeroed equal to a and b, because remember, those are the only two coefficients that this least squared method is solving for. And then we are going to once again define our function right in the style that we have up here. So our polynomial function without intercept, we have fx equals a times x squared plus b to the x. And then as we are defining it, we also see the operators that we learned before, right? Our exponent operators, our multiplication, our addition operators. And we're going to set that equal to our y fit. Also, we have our x fit here that we previously described over here in this line of code. We're going to have the same x fit. There's no reason to define another one. And we're going to plug that back into our x fit zeroed, which again, keeping in mind, you want to keep our variables nice and specific so that we know exactly what we're using and why. And then finally, we're going to be plotting our x and our y here using ax.plot. And we are going to label it so that we can see it in our legend. We're going to label it zeroed polynomial fit. And the last thing we're going to do before that is we are going to print out what our normal and our zeroed polynomial coefficients are, just so that we can see them ourselves. And so now we have our polynomial coefficients, we have our figure, we have our legend, we have our normal polynomial fit and our zeroed polynomial fit, and we also have our simulated data. So we have reached all the way towards the end. We've done a lot. Thank you guys for listening the whole way through and hopefully following along. I hope everything was super clear. But before we finish, I'm just going to summarize really quick what we did. So we started off with some very useful, important functions. We started off with the print function, the type function. We described different data types in Python. We looked at basic arithmetic operators. We also got a chance to look at data structures, as well as looking at how to assign variables. We were even introduced to some basic ideas in mechanical engineering. We got to look at some imported data, we got to analyze it, and we even got to perform some very basic machine learning techniques on our data. Hopefully you guys took away a lot, and I hope you enjoyed this intro to Python. I had a really great time preparing it and presenting it. So thank you, Mia, for arranging all of this. And now that there's a little bit of time, I'm here to answer any and all questions you guys may have.
Feel free to drop any questions in the chat, or you can also raise your hand and we'll call on you. Yeah, thank you guys so much for attending. I hope you guys learned a lot. I definitely learned a lot. I was not very familiar with Python coding before. I typically code in R and MATLAB, so this was really educational for me too. I had a good time. All right, we're going to give everyone a couple minutes to maybe ask questions if they have any, and then we'll wrap everything up. Okay. Well, it looks like nobody has any questions. Great. That means we did the right thing.
I hope that means everyone
I
understood
hope that
everything.
means that this was so
Hi, I'm so
clear. Oh,
sorry. Will you be sharing that Google Drive?
so
I
this
came in late, so I don't know.
Oh, yes. So there will be a recording, a full recording of the entire thing that will be
Okay.
available on our website. And I'll also be sending a link to the recording to everybody who registered for this.
Mhm.
So you will receive a full recording as well as the link to the collab to see the actual code and be able to play around with it.
Awesome. Thank you so much.
Yeah. Any other questions? Oh, there we go. Here are some questions. Okay. Um, Monica asks, what resources have you used to learn Python? Hmm.
Okay, so let me make sure yeah, I'm unmuted. So I started learning Python in high school. I took an intro class. It wasn't any like AP or special introduction. So that's where I was first introduced to it. But then going forward, I would say that I looked at some videos on YouTube. Mostly what I've learned has been what I've needed. So in my undergraduate research, I was working a lot with simulated environments. And so as I kind of went working through what I needed, I really just relied very heavily on information that Python has, a lot of Google searches. This was before ChatGPT, so I, I didn't have chat to ask. But yeah, so I really it was just born out of necessity and curiosity. Um, and I just really heavily relied on Google.
Eliza asks, is it worth it to learn coding in Python even if AI can do it?
Oh, absolutely. As I really try to emphasize in this lesson, there are some things that you can't, some logic that you can't code onto a computer. So, for example, we know that, just to take an example, a simplified example, but things like understanding that fuel input and electrical output must be grounded. And I understand that there are some things that chat can now learn as we put more information into it, but there will always be a threshold of human understanding versus computer understanding. So I'm a huge proponent and continue to learn coding, not only because AI can't replace you to a certain extent, but also because you can, code machine learning programs. So I think that it's still super important to learn these things, um, especially because it just gives you more creative freedom as well. So yeah, definitely keep learning coding.
Yeah, totally. I agree. Um, let's see. What is the best and easy way to learn Python and coding as a high school student? So, if we have any high school students here, what is the best way to learn coding for someone who hasn't yet gotten access to maybe college level courses in coding? I think you partially answered this already, but let's just reiterate.
Yeah, I would say definitely take any electives if your school offers them that has coding, whether that be AP or just like a regular coding class. You can join clubs as well in high school or in college, uh, or even I believe they probably have some sort of learning modules that you can do online as well. There's so many resources. I really encourage looking at what resources are out there, whether that be within your high school or just online. I think the internet has opened up so many opportunities and a lot of accessibility when it comes to learning coding. So I would encourage that.
Yeah, and I'm just going to add on to that at Research Girl, we're actually developing a Research 101 course right now that includes basic coding skills in all these different coding languages, including Python. So that's not available right now, but we're hoping to get it more off the ground this summer. So keep an eye out for that. If and when that is fully launched, it'll be announced on all of our social media, on our website, to our mailing list. So feel free to subscribe to our mailing list or follow us on social media to stay up to date so that you're notified when we do launch that program because that will be a really accessible way to learn coding and learn the basics of coding in a way that's accessible online without having to enroll in a class. So that's also an option. And then additionally, you can find all sorts of YouTube tutorials. There are so many like Reddit, or what would be better for Python? I feel like there's a better option than Reddit.
Probably Substack, I would.
Substack is great. Yeah, for all types of coding, Substack is great. So you can learn tons of the basics of coding in all these different languages through just reading about it, trial and error. I think the best way to learn anything is to get your hands dirty and try it yourself. So that's always a great place to start, especially if you're a high school student and you might not have access to college level coding classes. Yeah. All right. Any last questions before we wrap things up? Okay, I'm not seeing any in the chat. Well, thank you guys so much for attending. I'm Mia, I'm the CEO of Research Girl, and we host workshops like this. We're trying to host them more often. So if you want to get notified, like I said, when we do more workshops like this for different research skills or different coding languages, you can sign up for our mailing list, or you can subscribe or follow us on social media. So yeah, all of our resources are supposed to be free. So just like this, you just sign up and you can get free educational resources through us. So thank you so much for attending. I hope you guys learned a lot, and please have a great rest of your Saturday. Enjoy your weekend.
Thank you everyone for joining. Thank you, Mia. Again, this is great.